Yes, awesome. Now today, well, before starting, I hope you had a great week last week, your first week of the year regarding academics. I hope that everything is lining up pretty fine with your studies and everything is looking bright and good. So to begin with, there has been some delays in me uploading some materials like last lecture's presentation. I will do that today. I have having some issues with Moodle and the type of content I want to upload, so I apologize for that. And I hope that everything is fine today. So Robert wants to start. All right. So today we'll start with our first chapter, which is state of stress. And this is a very fine chapter, I would say. This lays the ground or the base, the groundwork for everything that we're going to do here, because in most of our topics, we're going to deal with calculating stresses. That's not so much what you did previously, but previously you calculated velocities, positions, accelerations, work, energy principle, or kinetic energy, potential energy, and vibration, and so on. But in this case, most of our course is dealing with stress. And the type of stress that interests mechanical engineers and those interested in mechanical engineering, because I noticed that we have people from other degrees in this course, which is a core course for mechanical engineers, I would say. This lays the foundation for many things. So today we're going to kind of see a few things about why we're taking a look at this state of stress. We're going to take a look at stress tensor. So why do we need it as engineers practically? Then we're going to talk about how to say if a stress is positive or negative. And this is very convenient, I would say, and it's aligned with many of your previous studies in mechanics where a force is positive if it goes up or down depending on the Cartesian reference system or let's say assumptions you made. So we need to define if something is positive or negative. We're going to talk a little bit about equilibrium conditions and what information brings us as in the process of determining the stresses. Stresses on an inclined plane, this is going to become more evident when we jump into this area here. We're going to talk about principal stresses, which is, I would say, the main, if I have to say what's the most important part of this whole lecture, I would say is principal stresses, because this is what we are after in this lecture or in our, let's say, discovery process. And finally, let's see, I think this is going to be a short lecture, but as I talk a lot, it might be possible that we extend, and I hope that we have time to do this exercise, problem exercise, or however you want to call it. Yeah. So this is what we're going to be looking at today. But before that, do you have any questions regarding the course in general or something you want to bring up before jumping into the lecture? Please write it in the chat and I will take a look at it. All right, so let's move forward. And introduction. So this is a pretty fine picture, I would say. I don't know if you recognize this picture here, this one here. What is this? Actually, this is something, I don't know if you had any course related to this, and more specifically, a practical course. I did have the opportunity in my times to do such a course, in the sense that it was a course that was given by the metallurgy department, so it was obligatory for us to take it. And what you do, for example, this probably is a metal, steel. Let's imagine that this is steel. I would say yes, probably it is. And what you would do is that you would cut a piece of steel, and let me see if I can pull up a picture. Lithography profit. Let me see. Like this. Yeah, this is a pretty good picture. I'm going to put it temporarily here. Yeah. So what we would do is I will just put it here and then remove it. So you would cut a piece of metal, the one that you wanted to study, and so basically you would then cut it, embed it in this resin. This is a epoxy resin, and then you would polish the face, but you would polish like a mirror polished, type. Then after you had this, you would put some liquid, some chemicals, we call it reactive, which are kind of some sort of a oxidating or corrosive agent, a little bit corrosive agent. And what you would end up after you put it under the microscope, yeah, my computer is lagging a little bit. We put it here, nice. It would be something like this, yeah. So this would have different shapes, typical shapes, typical sizes, and you have these black parts here. You can see actually these small lines. If I make a little bit of a zoom, no, I cannot zoom it. Actually, I lost the, if I go up or down, yeah. So a little bit of these kind of things. So these kind of gray areas are called grains. Yeah, these are the grains of the material. This is what forms the material itself. No, these are grains. And then these spaces are called kind of interstices or something like that. And you can see that a material is not completely continuous. So all matters in nature are not uniform and discontinuous. So what we see as steel, as a shaft, as a beam, as any machine element is in a microscopic level is something like this. Yeah, so it's not continuous, which means that this may be a little bit difficult to understand what's happening with these materials once this is, affected by a load, a moment, a torque, or something like that. So you just start getting the grip of it. So more interesting about this process here is that depending on the thermal thermal treatment that you apply to the steel, you're going to have larger grains, smaller grains, and depending on the size of the grains, the size of these impurities here, so you're going to have certain characteristics on the steel that are going to define or determine, for example, the strength of the material, elastic properties of the material, and so on. So this is marvelous. This is fabulous in the sense in the engineering world because this is what we have. But on the other hand, it gives us the idea things are pretty complex. Yeah. So as we cannot predict how these shapes are going to be formed, I don't know. I wouldn't know how to tell if this is going to resist any loading or not based off just looking at this. So I have to make assumptions. So that's why we have a few assumptions here. And one of these is that we're going to consider that, forget the reality, and we are going to consider that everything is continuous. So everything is a big grain. There are not impurities, there are not no lattices here, there is nothing here. So everything is, let's say, continuous. It would make our life easier. Then any forces that are applied, or are needed to be transmitted from one point to another. So, we're going to say, they can be transmitted without any interruption in the process, meaning that if I wanted to point something like this, that there is a force, something like in here, a force here. So this force can be, just travel along any path if it decides to do so. So in this case, this is some of the assumptions we're going to make. Yeah, but now the question is how, okay, I made those assumptions to reduce complexity, but how then I can predict that something is going to break or not if I'm neglecting the obvious that, this is not continuous. Well, then we jump to something that is called the phenomenological approach of studying things. Yeah. So what engineers are interested is in something called rheological properties of the material. So rheological behavior is basically the capacity a fluid has to deform or to flow. Yeah. But then when you apply this to metals, for example, basically what you're saying is that what's the capacity of this steel, this solid part to deform, basically. Yeah, we can move it or apply, decontextualize, the rheological behavior of a fluid to a solid. But now, the phenomenological approach, which means is that, let's imagine, they would say, let's imagine that you have a black box, which is your machine element, the part, the shaft, or anything. Yeah. And then you are going to apply some loads. So one force here, so you're applying another force here, and maybe a moment around here. Yeah. So you don't know what happens inside of this. Yeah. But then what you have to do is say, okay, what are the consequences of this? Yeah. So what are the consequences of applying those forces? So is this going to deform or something? Well, if it's going to deform, then you can see right away what are the consequences of these forces. Yeah. So the phenomenological approach means that it doesn't matter what happens inside. What matter is are the consequences of the forces in a visible way. For example, if I apply these forces and these deforms, then I measure the forces and I measure the deformation, and then that's going to tell me, hey, you know what? Every time that I apply this force here, yeah, then this is going to deform something like this. No, it's going to deform something like this. So this deformation here then is caused by these forces. So every time that that happens, this deformation is going to happen. Then I can start putting, 2 plus 2 equals 4 in the sense that, these forces affect the material in this way. So we start measuring things. Even when we do some testing related to, actually, tensile testing, yeah, this is a pretty fine picture. I'm going to bring it, actually, yeah, this one here. A couple of pictures I'm going to bring. So this one here, too big, so let's put it like this. So this is a tensile test that is performed by this machine or a machine of this type. Let me bring the machine. This one here. So you put this test specimen in between these two clamps, and then you start pulling apart those two clamps until it breaks. Depending on the type of material, if it's brittle of ductile, then you're going to have a type of practice type of breaking. But just by looking at that, I apply some forces to this test specimen here. For example, tensile would be a tensile force here. So I apply a certain amount of force, and that failed like this. They broke, then say, this is what's going to happen. So this is the way we engineers approach many things where or when we don't know what is exactly happening inside of the piece. So that's what we call the phenomenological approach. Do you guys have any question before moving forward? Let me then move this to the side. And then let me just delete this or remove this. Oh, this is in the front, maybe. Can I do it now? Yeah. Yeah, delete all of this. All right. So this is the way we approach things, or many of the things. And I don't know if you have noticed this, but this is a pattern that keeps repeating in your courses. That well, we don't know exactly what's happening there, but we do know that when we do this, this happens. Yeah, great. Now, uh, this state of stress is represented by something called the stress tensor. Yeah, but then I don't know if you have a chance to see what is a tensor. And basically, when we try to describe numbers in our mathematics applications, so we can deal with scalars, which is just a number. For example, here I just draw these pictures. Temperature 38. This person is 18 years old. For example, that's a scalar. It's just a number, and you know that. Now, when we talk with vectors, so it's kind of we are augmenting, so we are increasing the information a number can give us. For example, this gives us just a number. Yeah, vectors does not only give us the number, but give us something else, which is, hey, you know what? This rocket is traveling at 1,000 kilometers per hour, and not only that, it's traveling in this direction. Yeah, so it's kind of, if this gives me the name, this is giving me the last name. Name and last name. So imagine, look at that. So this is the way it is represented. But then we got matrices that it is kind of, that if we group a bunch of people and say, well, this is John and this is the last name, this is Tommy, this is the last name, this is Joseph, this is the last name. So you start, piling together vectors. But then a tensor, all of these are tensors. But a tensor, a little bit hard to define, but you can take this definition home and say, well, tensor is just an array of number of functions arranged on a regular grid. That's it. You could think of a tensor as a matrix, yeah? And when you see, well, a scalar is just, for example, if I write down here 18, so a vector can be, if I write it in 3 dimensions, can be something like this. It's going to be 3, 4, 5. But then a scalar, sorry, a matrix is going to be something like, a little bit more wider. And this is going to be, well, it's 3, 4, 5, 1, 3, 7, 9, 10, 11. So okay, so we don't know that. But these are tensors. Tensors have different rules, that mathematical rules that you need to use in order to operate with them. But then the way we're going to form our state of stress is represented by using a stress tensor. A stress tensor resembles something like a matrix, a 3 by 3 matrix. Yeah. In your courses, if you see any stress specification, you would have an element, something like, let me see if I can draw a more or less decent square, and you would say, well, you know what, there is a sigma x here, there is a sigma y here, and then you have certain or other stresses. This is tau xy and something like this, yeah, tau yx, or the other way around, I would say yx, and this is xy. And then, of course, this repeated, write a bit more decently, y, and then this one here, sigma x, and then again these dudes here, tau xy, and then this one here. You might have seen this one here. Yeah? But now we are not talking about this. We are talking about a three-dimensional case, which means that this needs to be expanded, augmented. And for that, we need to use a thing such as stress tensor to represent the state of stress of a point. And you would say, well, why do we need that? Well, this is what I'm going to show you next. Why do we need this? So why are we taking a look at this? Is this important? Is this something that I might use in the future? Well, if you're going to work with design regarding mechanical engineering, or your work in the future is going to be involved with research of failures, or designing beautiful things mechanically and this kind of stuff, you need to know a little bit about this. Yeah, because as I mentioned in our last class, we need to be aware if something is going to break, or if a material is going to fail. And I define for our course, you can take any other if you want, but in the definition that I choose for the course is that something is going to fail if it breaks or if it deforms beyond usable range. Yeah. So if it breaks, obviously that's not going to work any longer. But if it deforms, it might be the integrity of the part. It might be okay, but it might not be usable at all. And what do I mean by that? Because we have a body of standards or situations where you say, or we can say that if the deformation is more than this, then this is not going to work. And what do I mean by this? So let's imagine that we have let me see, a beam. So there's a beam here. I should try to use the ruler so it makes a little bit more decent lines. Yeah. So imagine that you have a beam here, like this. And this beam doesn't matter how it's supported, but it's supported somehow to the ground. So let's say that this is supported by simply supported beam. Yeah. And let's imagine that on top of that beam, which is part of a floor of a factory, you have a motor. I'm going to try to draw a motor here, electrical motor, something like this. This is the shaft. Then you have a coupling, something that couples the rotatory movement of the motor with, maybe, let's put it this way, maybe a pump. Yeah. So a centrifugal pump. So something like this, and something like this, and then you have this one here. This is a motor, and this is a pump. And this is part of some design you're doing. But what about if when this motor, let me write a little bit more here, so it has some veins here that helps with the heat dissipation, and then you have this one here. We move this just a little bit. I just wanted to move it like this. Yes, and then I have this one here. There's a pump. So what about if when you mount this equipment on the beam, and plus on the other equipment that might be there, this beam deforms like this, where if I make this line like this, again, let me use it's so sad I cannot add more of this. If this is the neutral line, so this is going to deform something here. Yeah. So what do you think is the adequate value of this deformation? So you have to ask a couple of questions first. Is it adequate for the beam? Yeah, maybe it is adequate for the beam, so the beam is not going to suffer. But what about these two dudes here? Is it enough for this? Because what might happen is that if I take a close-up of this area here, is that maybe the motor, this is the part of the motor, the shaft, I'm going to exaggerate this. And this coupling, this is exaggerated, okay? Happens something like this. Again, this is motor, and this is pump. That is going to impose so much stresses in the bearings of the motor and on the bearings on the shaft, on the pump, that they would work, but they will fail prematurely. So this is something that the deformation of something is even more important than the fact that it's going to break, because you may trust that deformation is fine enough, but then what you're going to be doing is just deteriorating the equipment mounted on top of that. So this is why I have defined a failure of a solid material. If it breaks, that you can see right away that it broke. But if the deformation is going to have, it is the correct one. So it doesn't change the limits. It doesn't affect the functioning of the machines here. And what I said, that there's a body of standards that tells you, hey, if you're going to calculate such beams and you're going to mount certain things, try not to exceed these maximum limitations. And then you have to take that body of knowledge. So those are experiments, those are experience-based, let's say, information that you have to bring it. So you say, well, you know what, in the past, this has failed, if this works under these conditions, so we need to change it. So this is why we need this. Yeah, this is why we need to understand this. And definitely this is a combination of what stresses are, strains are, and then that forms a state of stress. What questions do you have? Let's continue. Let's continue then. Now, this is something that I wanted to draw that is pretty similar to the metallography specimen that I showed, which is this one here. Yeah. So what we can see, according to the phenomenological approaches, that we can see the forces, surface forces, point loads, moments, and any that you can occur, temperature, whatever, body forces, pressures or whatever. And how do these dudes, let's say, react? Because these are internal forces here. Yeah. These happen to be these internal forces that are keeping the material together. So these are internal forces. So how they're holding up? Are they strong enough to, or the forces are larger than the ones that they can kind of support or something like that? So this is why we need a stress tensor. And then how do we come from reality, from a practical experience, to this mathematical abstract world? So let's take an example here. So this is a familiar, I would say, thing that you have seen. So we have a beam, we have columns, we have other smaller beams. You join the beam with the column using this volted arrangement. Yeah. And then when you say, well, is this enough? Is this going to fail? You say, well, to understand if it's going to fail, I need to go to the inside of the material and pick a point and see if this is going to fail or not. Yeah, I need to see what are the stresses at any of these points here, kind of in here, or in here, or here, or in any part. I need to check if the stresses that are going to be generated or developed in any of these points is larger than the strength of the material, and then hence the material is going to fail. Yeah. So is this one, in this one. So if we already assume that this is going to be considered a continuous element, so I want to ask you as a kind of as a reflection, kind of just to reflect on this. How many points do exist in this beam, for example, in this piece of beam shown in the picture? Now, how many of them? Well, there are an infinite numbers of points that you could choose there. Yeah. And then how do I get the points, or how do I know, how do I make sure that when I pick a point, I pick the winning point, meaning I pick the point where the thing is going to fail and not the one next to it. You see? Then when we pick a point, I'm going to come back to this thought a little bit later, but when we pick a point, and let's imagine that I picked this point here, yeah, an infinitesimal point. When I tell that is an infinitesimal, it means that you cannot see it. It's just too small that you cannot just see it. Yeah, and this is what we have here. So this is the, imagine that this is a body, the beam. You cut it, or this one, and then you pick a point. Yes, and this small cube actually is called in the literature parallelepiped. So I'm going to call it cube because it's shorter. So when you see this cube here, this cube, due to the forces applied to the beam, there are going to be stresses appearing, affecting this cube. Yeah, and I just draw the cube larger here. Then you're going to have, if you take a reference system such as this one, and this one here, then you're going to have stresses in the x direction. I'm going to call it, start calling it like this, stresses in the y direction. Yeah, maybe stresses like this. These are called shear stresses in this direction. Yeah, and these stresses are formed using a technique that I think you used in mechanics too, meaning that if you have we're going to also repeat it here between the third and fourth, when we see failure theories, that when you have loads applied to a body, those loads develop stresses, but are they normal stresses? Are they shear stresses? And where are they located? Well, we're going to see that. So, but then, this cube and all the faces of this infinitesimal point in this parallelepiped, in this cube, there are going to be stresses in most of all of this. Yeah. So you're going to have stresses here in the z direction and so on. Yeah. And then coming back to ideas of which one do I take, and reflect on this. Not only this, because I chose the orientation of this parallelepiped in something like this. Yeah, saying this is x, y, for like this, z. But what about if I rotate a little bit this? Let me see if I can rotate this. Can I rotate it? No, I cannot. Or yes. What about if I rotate this cube? Yeah, let me just try to grab this complete like this, and then copy, and then I'm going to paste it as a figure, as a picture. Yeah, do it smaller. So, but what about if I just, it's not letting me do anything. Just bear with me. That sometimes my computer is. Can I? No, I cannot rotate. Oh well, just give it a time. Give it a few seconds. So, which means here, let me come back and here, let's see if now it gives me. Yeah. So what about if I choose a different coordinate system, like this one, oriented like this? So now the question is not only how many points do I have, or could I choose to determine where it's going to break, but how many orientations? So you have infinite number of points, you have infinite orientations. Well, not, yeah, infinite orientation, I would say, if you want to go to very small levels. So we will go crazy, isn't it? So doing this by hand, uh, unless you know the application, and the application you are designing is always the same and you're a specialist in this application, well, you could do it by hand. But no, what people do, well, people start using finite element analysis. And let me bring one example here. And this is, for example, this is some sort of hook, or not hook, but support. Let me check something, what's happening. I'm going to fix some properties here. Just give me a second. Meeting option, because there are people opening the. Okay, we should be fine now. This one here, copy image, and then this one here. So we start using software, and this software, for example, finite element analysis. This is instead of support or kind of pin handle or something like that. And then what you do is that you start dividing the part into different points. So each one of these parts is a point where the finite element software is going to calculate stresses. Yeah, these are points. So you say, well, why is this? Well, you know what? These are points, but you don't need that many points in this area because this part won't probably fail in here. But please put more points in these areas because this is where most of the time this fails. So you want to make sure that you get the point, yeah? And then this can be as dense as possible, meaning you can put millions of points here and run the software. And not only that, the beauty of this is that between 2 points there are, if you're going to study finite element analysis, there is something called interpolation functions that tells you, well, more or less the stresses can be approximated between 2 points if we consider that this happens and so on. So you can have a guesstimation of what are the stresses in between points. Yeah. And then you get these beautiful images. Let me bring another one, for example. Yeah, this looks nice. Copy image. Let me get rid of this one. Something like this, you see, where you are color coding. For example, if it's red is where the most stresses or deformation are, and so on. You see, for example, in this case, near the hole here, and then is this part, maybe because this is being bended or something like that. So we start using that, and then we start delegating this whole thought process of where should I calculate stresses to this. But you would tell me, but then why do we need to learn this part if we have a software that can do it right away? Well, the reason for that, my friends, is that if you don't know this theory, you could be assuming and trusting blindly on what the software is doing, and then whatever results the software tells you, you're going to consider is the truth, which means that you are prone to make big mistakes. For example, in just something advanced, I hope that you get to see this in master studies if you're going to continue or more research, is that depending on the type of forces applied to it, depending on the type of element, machine element, so certain meshing, this meshing is the process of dividing this into points, like doing this is meshing, are more prone to tell you the truth than others. And then, for example, these are triangular elements here, then they can have problems with this type of application, which is going to tell you only half of the truth, and then you are going to blindly select this. So that's why you need to know a little bit of theory before jumping into software blindly to judge my calculations. So we need to do it by hand. And the good thing here is I'm going to tell you, do it in here, do it in there, and then you don't have to be guessing where to do it. Any questions so far? None? Then how do I transform this into a tensor, a strength tensor? So imagine that we have this element. I'm going to draw this one here. So I have a normal stress pointing out this one here. I'm going to call it 10, and then I'm going to call this one 20. I'm going to call this one 30. I'm not going to use any units. It could be megapascals. It could be kilograms per square centimeter. So any stress or pressure unit can be used here. So, but I'm not going to write them down here. Yeah. Then, of course, because of the symmetry of all of these, they're going to have 10 also here. And the bottom, you're going to have also here, you're going to have 20. And then in the back, like this, you're going to have 30. You see how this has to be in equilibrium. So, and this is something we're going to talk in the in the next slides about the equilibrium. So this equals to this equals to this, and this equals to this, because as this is a static structure, it doesn't move anywhere. So even though these are stresses on this area represent a force. So you cannot have different forces, because then it would mean that this might move and this is not moving. Yeah. Even though there are certain considerations where definitely there is a difference between this and this. And then you're going to have certain shear stresses, so such like this. I'm going to call this 5, and then this stress like this is 5, and then let's continue with this. And then in the bottom, something like this, like 5. and then on the top, something like this, like 5, and so on. Yeah, then you can have also other stresses, shear stresses in this direction, or in this kind of like this, or in this direction. So you see, this form a three-dimensional triad here. So that represents everything. But how do I take all these numbers and write it mathematically so I can use it? Well, this is where the representation of the stress tensor comes. And sometimes it's just represented by a sigma, yeah? And this sigma is going to be drawn, or this tensor, as a matrix. And this matrix is going to be written like this. So the first one is going to be xx, and I'm going to explain this nomenclature. This is going to be, I believe it's this, if it's x, y, and then this x, z, then this is going to be y. No, this is the other way around, sorry about that. But you are going to see how easy this becomes. Then this is going to be zx. This is going to be xy. This one and cy. And then final row is going to be this one, and this one. I hope you are taking notes. Now, what does it mean, these subindices? For example, let's take this shear stress yx. Yeah. So this y here represents the phase where it is applied. For example, this one here, let me write it down here, is considered to be the y phase. You don't need to start the recording because I'm recording this. So please stop the recording here, somebody. Yeah, I'm recording this, so don't overload the system. Thank you. So this is the y phase. Yeah. And then it follows also the other, let's say, the other phases. Now this is the x phase, and then this is the z phase. So whatever plane is perpendicular to that axis, that's the phase, y phase. So this one represents the phase, yeah, the phase. And these ones represents the direction of the stress, yeah, direction. For example, and let me clean up a little bit this, so we can do it with this. So this one here is a normal stress because it's normal to this plane, and the name of this friend here is sigma xx. Sometimes I could write it, or we could write it as sigma x, as a simple shortcut. Yeah, and it means that it is in the x phase, yeah, and then it points it in the x direction. So that's why here. Now, if I have this one here, let me come to another color. This one is going to be who? Well, is in the x phase because it's located in this plane here, and is pointing in the y direction. Now, what happens with this friend here? Well, this is total shear stress because it's parallel to the plane, and then it is on the x phase and pointing on to the z direction. Now, this is the way it is formed. Any questions? First row, second column? You mean first row, second column, this one? Yeah, sorry about that. This is a Y. Yeah, no, thank you for asking. Let me just, it's good that you're looking at it online, because if you see it as a replay, my bad writing. Yeah, X, yeah. Yeah, thank you. Yeah, and it continues like that. So, for example, this one, well, this is still XX, yeah? And for example, this one here, let me just delete all these dudes. this one coming out of the Z phase. Well, this one is a normal stress like this. Yeah. And if I wanted to represent this stress here, this is going to be a shear stress that is located on the Z phase and then is pointing upward to in the Y direction. So this is going to be Y. And this is the way you form the stress tensors. Yeah. Any more questions? Now we're used to say, well, you know what, this is the positive direction of this axis. Yeah. But what happens with this one here? So why are you writing it without a negative sign if it's pointing in the opposite direction to the positive convention we have always used? Well, there's where it's called the sign convention we were talking about, and that's called the von Karman convention. Yeah. And this is a recent convention, so we're talking about 100 years old, and that's young. That's a young convention for a mechanical concept, mechanical theory concept. This is a very young age. So it's pretty simple. Stresses are positive if the positive phase. So if they are in the positive phase, on the positive phase and point in the positive direction, and also positive if they are on the negative phase and point in the negative direction. Contrary to this, is negative. So what does this mean? This one here that I draw before. Let me see this one here. So this is positive because a positive phase, for example, if I have the reference system as this, then let's assume that it's in the middle. Yeah. But it works even though if it's not in the middle, even if all the phases fall into the positive side of the x-axis. Yeah. So this is in the positive phase, and then it's pointing in the positive direction. That's why it is positive. Now, in this case, in here, this is also positive because it's located on the negative phase and it's pointing in the negative direction. So both of these are positive stresses. And this is the von Karman convention. Now, what is a negative stress? A negative stress would be something like this. So this shear stress is what? Well, it's going to be, let me write the subindices. It's going to be xy, yeah, and it's going to be negative because even though it is in the positive phase, it's pointing in the negative direction, kind of to the convention that we have used before. That's why this is negative, like this. Now, if I wanted to represent it like this in here, so this one is also xy, and it's also negative, even though it's pointed in the positive direction because it is located in the negative phase. It needs to be pointing in the negative direction to be positive. So this is the von Karman convention of things. It's pretty simple. Whatever is contrary to these two things are let's say, let me just, are negative. Why is it be here? Yeah. Let me bring this one here so to have it as a reference. So, yeah. Okay, are we ready for our first quiz? Please go to Moodle, and if you don't see it, you are going to see it soon. Refresh the page. Just give me a second. Quiz 1.1, and the question is like this. You have about 5 minutes to do this, so take your time. So I'm going to put back this sign convention, but according to that, just tell if this box, so let's explain what's happening here. So just tell, you have just to tell if it's true or false that this is the correct, let's say, signing convention for this cube. And let me just explain this. So you have this cube, and then you have the red ones are the, the kind of the how the stress tensor is constructed, but okay, these are normal stresses and these are shear stresses. So these three correspond to the y phase, these three correspond to the negative y phase, these three correspond to the x positive phase, and these three correspond to the x negative phase, and so on. These three correspond to the negative z phase, and then these three correspond to the positive z phase. So look at this, the arrows were pointing, look at the stress tensor, knowing that these are, no, these dudes here. Actually, I should bring it again here, maybe. Yeah, I have it here. I'll also take into account this, right? So we can have everything in the same slide. And see if this is the correct representation of this cube. You have just to answer yes or no. And you have 5 minutes since you start, so this is von Karman convention. So you can start now if you have the question, ask. And when you start the test, you will have 5 minutes to give, well, 4 minutes, I believe, because this is very, very short. It's just yes or no. Analyze that. So in my computer is 1080-18. So let's come back at 1022 after you have submitted your answer. Back. $10.23. Go for it. All right, so we are back. Let me check. I have a question. I'm going to answer that in a while. So now, when you start a quiz, so you can when you click start the quiz, then the time starts running. And then if it's 5 minutes, 4 minutes, so when those 4 minutes, if you haven't answered that in that time, then you're not going to get anything there. Or whatever you press there is going to be submitted. So you can just wait a little bit before starting your quiz, read the question, analyze the problem, and then when you're ready, you can start the quiz. Yeah. So there are a couple of instances. First, you have the quiz time here. That once you click, then it starts running. So it could be 5 minutes, it could be 4 minutes, something like that. It could be 30 seconds, 10 minutes. Yeah. And the other time is the time I'm going to give you to answer, meaning it's kind of the, what's the name for it? I'm going to tell you the exact name for it. It's called when the open time. Yeah, be first with this. So what this means is that, I tell you, well, the quiz is going to be open from 10:20 till 10:30, for example. This is the open time. But you have, once you click start doing it, you have 5 minutes to do the test. Meaning when you click that, then it says time limit for the question. What is this? That between 10:20 and 10:30, you have in that slot 5 minutes to answer your question. Yeah. So it's not going to be open indefinitely, meaning that you come at 12 and do the quiz. No, it's not going to happen. Now, let's see. That's why you run out of time. So be mindful of that. And the other one, I'm not allowed to open. So please consider that the email you are using, yeah. Then if the email is not associated with the Moodle, then it might be possible that you are not, they're not going to register your answer because it's the formal email you use for Moodle. So if you have a LUT account and you log in using your Gmail, for example, because it's easier for you, then that Gmail is not registered as a user of this course, as an enrolled person of this course. So make sure of that. Yeah. And then that's something that might happen. And when it's not allowed, it's because the open time expired. So when I said that we were going to come back at 10:23, it's because at 10:23 closed the exercise. So let's do another quiz to see how it goes. For example, I get people try to access the room that said that they're not verified, But if you don't have the LUT account, so it might be something like that. But anyway, just two people were left without attempting or something like that. Now, for this one, you have 5 minutes to do it. It's very easy also. What you need to do is take this stress tensor and this cube and write the stress tensor, meaning what is the written part here. So you need to write down the stress tensor from this, yeah. And what you're going to do is that you're going to have numbers here and so on. And you need to see which of the options is the one that you think is correct, or is similar to your let's say, your stress tensor. Remember that this is written like this as a simplification because everything that happens in this phase happens also in this phase. For example, this one here is also like this. This is 20. And this like here. No, yeah, you have all the quizzes are available regardless if you pass the first or not, or you get grades. It's not that you pass, it's that if you get grades or not. And then you have this one here. Yeah, this is 30. And then this one here, this is 10. So remember that what happens in here happens in the bottom, what happens in here happens in this phase, what happens in here happens in the back phase of this. Just write the stress tensor that corresponds to this infinitesimal cube and then compare to your options. You're going to be able to yeah, I will do that. I will do so. Let's do so, but it's not related to this, so that's why we can. Now you have 5 minutes. The quiz is open, so go to the quiz session in Moodle, and you're going to see that what they have or what you have there is a series of examples, and then just pick the one that you think is the stress tensor that corresponds to this infinitesimal cube. Now, once you start the quiz, you have 5 minutes. So it's 10:31 now in my computer. So you have until 10:40 to, it's going to be open in this time. Try to do the second one, please. If not, it's something that is messing out. Right, even though the time is not up, I think it's safe to go because I see that most of you submitted the quiz, so there was no any issues at least submitting it this time. Still a couple of minutes open. So let's go to this one. Let me just delete many things here. This and this. So what's the answer of this? Is it true or false? Well, yeah, it is. So if you follow these lines, for example, you see, let's analyze, for example, this sigma x. Remember that I can write it like this, or I can write it like this, just for simplicity. Sigma y and sigma z. So I said this is positive. Yeah, this one is positive. Sigma y, normal stress in the y phase is negative. Yes, it is negative because I am in the positive phase, but this vector is pointing down. Yeah. And then the sigma z is positive because, it complies with von Karman convention. Now let's see, this one, this is tau yx, yeah, and then this is negative. Well, yes, it is negative because you see this dude is in the positive phase and pointing in the negative direction, which means that this is negative. Now this one here, who is this? This is zx, meaning this one here. So, well, this is in the positive phase and pointing in the positive direction, kind of resembles this one. So It's true. Yeah, this stress tensor corresponds to this representation here. Now, why did I want to uh, create a quiz out of this? Because if you form this and don't write correctly the stress tensor, then everything is a downfall. No, calculations are bad. So it's a simple thing, but we need to make sure that we're writing it okay. Yeah. So so in this case, yeah, this is true. Any questions about this? Those who were asking to go over this exercise? Now, if we go to the second, so let me bring here the image. You had something like this. So I hope nobody wrote down letter E because actually it does exist. So let me see. Want to kind of just two people got it wrong in this one. The rest got it perfectly. Nice. Let's see. Actually, the answer I believe is the first one. Why? Because this is sigma x, which is this one here. This is sigma y 50 positive, this one here. This is sigma z, which is positive, this one here. So perfect. So this one can match that one. This one matches that one. These two, they do not match the diagonal terms represented by the normal stresses. So these are a no. These are not possible. And these are not possible, and these for sure are not possible. Now, let's take a look at the shear stresses. So for example, I know that these two are positive, but what about this dude here? This one is tau y z. Now it's in the positive phase, but pointing in the negative direction, which means that this is negative. Look at this. And this one. Okay, so okay, this is matching, but what about this one? So this stress which corresponds to zx, is it positive or is it negative? Well, zx, which is this one, is positive because it's in the positive phase and pointing in the positive direction. So it's positive, which means that this cannot be. So everybody got it right. No, it is the first one, except for a couple of people. But I hope that you get to see it. Yeah, just two people got it wrong. Any questions about this? Now, if you notice, let me bring back this, not this one, but actually I could take this screen capture of this one here. I can reuse this one. And let me crop it just to show what I want to show you. I believe you noticed that when we talk about stress tensor, these terms are pretty much the same all the time. This term, and this one are the same, and these two are the same also. So if you see patterns here, so most of the time you see how these are repeating. For example, this one repeats here, this one repeats here, this one repeats here. I'm muted. Thank you. Thank you. Did you get to hear this explanation? I hope you did. Okay, perfect. Now, yeah, in this case, for example, these are a pattern that repeats in the stress tensor, which is that these two are the same, these and these are the same, these and these are the same. And then I was mentioning that in this case, you see how the pattern repeats, that this one repeats with this one repeats with this one, and then this one repeats here. So, and this is characteristic of a stress tensor. This value repeats in different parts of the representation of the stress tensor. And that is thanks to something called equilibrium conditions. So when we apply rotation equilibrium and translation equilibrium, a few extra information appears. Yeah. For example, if we apply rotation equilibrium, by the way, I'm going to be leaving a link to a video where the detail of everything is posted, just if you are interested in this. I believe at this point, it's not that interesting for you to know the minimum detail of things, but the most important things so you can apply them. But even though, well, the video is there, I did it for last years and previous years, and I noticed that it was too much. Is that, for example, if I take the only stresses that causes forces that can make this cube rotate about the x-axis. For example, in this cube, only these stresses, this stress here. For example, if this is the x, this one here is the y, and definitely this one here is the z. I call it the dz because they are so small. This dude here, this friend, produces a force. Let's call it force zy, which is going to be that stress multiplied by the x and who else? And the z. Sorry, dy, dx and dy. So this is a force. And this force would try to rotate this cube around the x-axis. If we look at it like this, in the clockwise direction, this one in the counterclockwise direction, and so on. Yeah. So when we write the equilibrium condition in rotation for this cube, yeah, meaning that this produces a moment around this axis, this produces a moment around this axis, and so on, I'm going to end up with this relationship here. Which means that if I delete this, that the same stress, shear stress, YZ, this one here, put it in red, is equal to the one in ZY, this one here. And so on, this one is equal to Z1. That's why we have that this one, actually, if we talk, that this one, ZY, this one here equals to this one here. That's why it gets repeated in all in these places here. So that is called, or one of the consequences of applying the rotation equilibrium in this parallelepiped or infinitesimal cube. This is just example for rotation around the x-axis, but there are other two equations. There are the rotations around the y and z-axis, and they're going to produce something that is called the reciprocity of shear stresses. This one here, this one. That's why I was mentioning that that's kind of this one is equal to this one, and this one is equal to this one. So that's why, because of the reciprocity of shear stresses, is that this happens. So that is the first consequence. The second consequence is that in a stress tensor that I could really like, I'm going to copy this one. I'm going to put it like in here. If we consider this to be unknowns that I need to figure out, so each one is an unknown that I need to find out its value. So I'm not talking about 9 unknowns. No, I'm talking about 6 unknowns. Why? Because of the reciprocity of shear stresses. These are one unknown, these ones are one unknown, and these ones are one unknown. So we have 1, 2, 3, 4, 5, 6 unknowns. Yeah. So those are the two consequences of reciprocity of shear stresses. And I'm going to give you a tip. For the exam. Let me write it down here so I don't miss. I'm going to ask you as one question in the theory part. The question is going to be something like this. Write it down because it's going for the exam and you already can have the answer and you already have the point. So what are this, the two consequences of the equilibrium rotation or rotation equilibrium. In the stress tensor. So write it down because it's coming. So what are the two consequences? The first one, the reciprocity of shear stresses. And the second one, that instead of 9 unknowns, we need only 6. And this is the way you need to answer it. Instead of if when you see this is in the exam, when you see this in the exam, you just answer like this: reciprocity of shear stresses, and instead of 9 unknowns, we need just only 6. This is for the exam, so just write it down because it's coming. So let me just like this. There you go. Any questions? Right, so let's see what happens with the equilibrium conditions in the translation. Well, when we talk about the equilibrium conditions in translation, we need to do more considerations in the sense that yeah, we'll leave it there in the notes. So if somebody is interested to know what is in the exam, they would need just to look at the videos. All right. So let's see. So in this case, I mentioned, well, you know what? For example, let's take a look at this normal stress in X. Now appears normal stress in X plus something else. So a small piece of stress increment in the X direction. And you say, but John, you said that these two things, where do I have it? Yeah. These two things, this one here and this one here are the same. But why now in this direction is not the same, but you have the stresses, the stress in X, and then you have the stress in X in this side plus something. Well, because in reality, let's imagine that we're looking at a two-dimensional representation of this. And if we consider that this is a point, definitely we're going to have a stress in here, and then we're going to have another stress in here. But what happens with the adjacent point? Imagine that this is the adjacent point. Well, are you going to have also this one here and then this one here because, to follow the whole thing? So if we say that these in reality do not change, like this, oh boy, let me just get rid of this. Then it would mean that for any structure, you would have to understand that then the stress is going to be constant along the x-axis, and that's not the case. So if this is point 1 that you chose, and this is point 2, then if the stress increases from one point to another, so it's most probably that here, this stress, there is going to be an increment here, and that increment is going to be represented by this differential. Yeah, that is going to be then represented here with a different stress. So yes, across the point that you chose to analyze stresses, there are going to be differences in the same direction. Yeah, and thanks to those differences is that we get something that called the differential equations of equilibrium. So this is just in the, I believe this is just in the, where is it, in the x direction. So this is the sum of forces in the x direction that are equal to 0, where this x here is just a body force. So these are just differential equations of equilibrium that gives you that, meaning that if you know the equation on how the stresses develop across the length of the material, then you could apply these differential equations of equilibrium to discover what are the stresses at any point. And that's a very nice application of this. This is a lengthy procedure to go from this to this, but that's going to be in the video. In the video I'm going to upload another video, not this one, but I'm going to upload. So how do we get from here to here? Yeah, and this is very cool. So again, this is something we need to understand. Just to summarize, the equilibrium conditions in the rotation equilibrium brings us two things, which is the reciprocity of shear stresses, and instead of 9 unknowns, we need only 6 unknowns. Reciprocity of shear stresses means that these two friends are the same. This one is the same with this, and this one is the same with this. Yeah. Translation equilibrium gives us the differential equations of equilibrium, where if we know how the equation of stresses is formed, then we can know the stresses at any point of the length of the material, or on a segment of the material. Any questions so far? All right, so now, simple question, simple quiz. Quiz 1.3. According to what we just saw, yeah, reciprocity of shear stresses, rotation equilibrium, basically. Maybe this not, but this one. Yeah. Tell if it's true or not that if this element here is well written or not, if this stress tensor complies with equilibrium conditions. So this is quiz 1.3, and it is available now. So it's 11:03, and it's going to be open until 11:07 or 08. And you have a lot of time to do it, but you don't need the time to answer if this is correct or not. Actually, let's take until 10. So go to Moodle and just answer truth or no, truth or false, if this is the correct representation of a stress tensor that complies with the equilibrium conditions. And I'm going to put this one here. All right, let's come back to this. And looking at the results, 4 people got it wrong. So 4 people got it wrong, the rest did perfect. And the question was, just indicate if this tensor complies with equilibrium conditions. And basically I mentioned, well, we're talking about rotation equilibrium. That's why I showed this. And again, this has to be equal to this. This one has to be equal to this. And this one has to be equal to this. And they are not, which means that this is false. This does not comply with the equilibrium conditions. You see, it's just because these two numbers must be the same, and they are not. So 4 people got it wrong. I hope you get kind of the explanation why it's not true, it is wrong. It's because of, again, thanks to the consequences of applying the rotation equilibrium on a stress tensor, or on a infinitesimal cube, as you want to call it. So that's why this is false, because these two must be the same, and they are not, which means that they do not comply with equilibrium conditions. Any questions? All right. Well, actually, there were more people answering, and 6 people got it wrong. Wow. All right, so let's continue. Again, if already telling you that this goes to the exam, so please write it down, because that goes to the exam. Now, we talked in this part that, yeah, I chose representing this infinitesimal cube like this, oriented, around, or it's parallel to the Cartesian coordinate system, but it could be oriented in a different way, and there could be infinite numbers of orientations. So what is that important to us? Well, now to see the importance, we need to know how to express this stress tensor on a different plane than the one that we chose. So imagine that you chose this stress tensor, and let me copy it from here. One nice, maybe this one. Yeah, let me copy this one here. Now I want to paste it as a figure, as a picture, so I can shrink it if it allows me. Yeah. So I chose that one, but what about if I wanted to understand, oh, what happens if I just cut this dude like this? Yeah. And I take a small piece of this cube, and I try to understand what are the stresses after I cut this corner. What are the stresses that are formed there in that specific plane? So that's the help of something called stresses on an inclined plane, or how to do it. And to do it, again, there's more to it, and I will invite you to look for it. But not only you need to know what is the orientation of the plane, but the orientation of the normals and shear stresses, but also how to represent that orientation, how to talk about orientations. And something that we use here are these elements, this vector here, that these are called direction cosines. Yeah. These direction cosines represent a direction in space that when you multiply the stress tensor times that direction cosines vector, it would give you the magnitude of the normal vector to that plane. This one here. As simple as that. Again, the how to get to these formulas is very detailed, but I'm going to give you what you really need for your understanding right now and applications right now. So there are other ways to represent orientation in space, but the way that this has been standardized is by using direction cosines. And they just tell you a direction cosine. For example, if you have an XY Cartesian coordinate system like this is X, Y, and Z, and you have a vector like this. Direction cosines is simply kind of what is the angle, or this is you have an angle here, alpha maybe. Then here you have an angle between this vector and the y-axis, and you call it beta. And then you have an angle between the vector and the z-axis, and you call it maybe theta, like this. And then the projection of this vector on this axis is represented by taking the magnitude of the vector, let's call it t to follow this. So this would be the length of the vector from here to here, and if you multiply by the cosine of alpha, that's going to give you the projection of this vector on the x-axis, and you can do the same for the y-axis and the z-axis. That's why it's called direction cosines. Yeah, and it's a way of representing orientation in space. But the important message that I want to give you is that if you take the stress tensor and then multiply by this vector of direction cosines, it would give you these components, Tx, Ty, and Tz, that represents the component of the normal stress or vector to the plane you are studying, like this one. Yeah, it's a simple concept, yet it's a very, let's say, lengthy process to get to it and to see it. But this is what is important. This is the core of this. Any questions? Now, again, if I give you, or somebody, if you are interested in analyzing this infinitesimal cube in a different orientation, then the basis for that is to use these equations. Yeah, and these are called Cauchy equations, for the guy who came up with all this idea. Again, this is 100, 200 years old. And again, why would you like to know stresses at a different orientation if you chose this one already? Well, because of the reason of that question saying, is this the maximum stress that this point is really, let's say, supporting? Because again, there are three things that we have discussed. Oh my goodness. I'm sorry, I apologize for that. Thank you for letting me know that I was muted. So let's see. Well, I don't know where I started, but okay. But why would I want to know stresses on an inclined plane? Because, well, we have talked about two different things. First, on a structure, there are infinite points that I can choose, so I can calculate stresses. Yeah. Second, there are infinite orientations. So it's not that I have the dilemma of which point to choose, but which orientation to pick to represent my infinitesimal cube. Now, imagine that you pick a point on a structure. Yeah? Let me see if I have something like meshing a picture. Yeah. Oh, these are nice. These are nice pictures. Let me just bring one. Here there are so many that I cannot decide. Let's pick one. Oh, this is one. Imagine this. This is a brake assembly. Yeah. And this is mesh and everything. And then you're studying this part. So this is very complex. And I say, well, I'm going to pick this point here. Or in green to make contour. This point here. I don't know what's better, but this one. Because you think when we're talking about analytical solutions, meaning doing it by hand, you think, well, I think that there is where the maximum stresses are going to be, and I think that there is where this thing is going to fail. Yeah, and you pick this point, and then that point is represented by your infinitesimal cube. Yeah, but then you are remained with the kind of unknown. But I know that that's the place that's going to where that is going to fail, because typically, and let's assume that this is true, typically this break fails here. But is this the correct orientation? Yeah. Then you can start playing around with the orientations of this cube to see if these stresses are the maximum stresses you can find in this point. Because stresses, depending on how you orient in space this cube, you're going to have a value of stress or another. So this tool, where it is allowing you is to say, it's allowing you to make sure that the stresses in this point, or you're going to calculate the maximum stresses possible existing on that point. So this is why this is very important. Yeah. And let me get rid of this. And let me put it like in here. So that's why. So not only you want to pick the correct point, or the closest point to your assumptions about where the maximum stress are going to be, but you're going to make sure that the orientation you chose is the correct one. Yeah, that's why this is helpful. Then, of course, if you have a normal stress, or you have a resulting stress, any resulting stress, you can transform that into a normal stress to the plane and a shear stress to the plane by using, again, the projection of the resultant stress on the normal axis and the projection of the normal stress on the shear parallel axis. And this, again, applying these formulas, they are very simple in this way. Kind of, it's just a dot product of the vector that you get here, this one here, and then multiplied by the normal direction, or the direction cosines representing the normal direction, and you get what is the normal and shear stresses in that area. But again, you're telling me, well, no, this is nice because I know, but what's the point of this? Well, because it would be wonderful if I didn't have to go over a million orientations to see what's the best, but if we could calculate, having this stress cube, infinitesimal cube, what is the orientation that is giving us the maximum stresses? Because you would understand that if I can give you the maximum stresses, then you could take those values, to the bank and say, you know what, these are the maximum stresses. So use any failure theories that we're going to see in the future to say if that's going to break or not. So that's why we need to make sure that at the point that we're analyzing, we are getting the maximum stresses. And that's where the principal stresses come into play. Yeah. Principal stresses are named like that because, first, if you have a stress tensor, and I'm going to put it like this, yeah, the one that we already know. So you have xy. You see that now I don't care about writing this in the correct form or kind of order, even though I should, but because I know that the reciprocity of shear stresses is working on my favor, and this is yz, yeah. So this is my stress tensor that I calculated. But there exists an orientation of that cube that when you change this and rotate this, there is an orientation of that cube that is going to transform this into, let's call it like this, principal, into a stress tensor of this form, sigma 1, sigma 2, and sigma 3. And all of these values are going to be 0. And these are called the principal directions. So it means that I could find an orientation of this friend here to give me just a diagonal matrix where these values are going to be the largest ones that you could find on that point. And isn't that wonderful that I could just get it at once without any needs of be testing angles, orientations, or anything like that? Well, there is something called principal stresses, and those are the stresses that we are interested on. So all of this, what we have done so far, is just to let you know that at any point you pick in any design, here, 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 or here, there is going to be a stress tensor, and that stress tensor can be transformed into principal stresses, which are going to be the largest ones there, which means you are going to be sure when doing your calculations that you are working with the largest stresses. And we know that working with larger stresses is what we want there. One characteristic of the principal directions is that there are no shear stresses in that thing, meaning that if I get to draw that infinitesimal cube, something like this, for example, oriented, kind of, you're going to have only these stresses, sigma 2 and sigma 3, and that's it. There are not going to be any shear stresses. This. Okay? And now, who is sigma 1, who is sigma 2, and who is sigma 3? We're going to see how to calculate this, but I believe I have it in the next slide. But when you calculate the principal stresses, they follow this convention. Sigma 1 is the largest stress, sigma 2 is the second largest, and sigma 3 is the minimum one. So whenever you work with principal stresses, you know that sigma 1 is the largest stress, and sigma 3 is the smallest one there. How to calculate it? Basically, we do know, and I believe it's written here, that the stress tensor is a symmetrical matrix. When I say symmetrical matrix, is that the lower half equals to the upper half. That's a symmetrical matrix. You can invert the symmetrical matrix, yeah? And they say it can be diagonalized. It means that you can find the principal directions. That's what it says. So how to do that? So I'm going to leave you this, but basically there is something called the characteristic equation of the stress tensor. That is this one. That if you say, hey, you know what, I want to know what is this vector. This vector is a matrix like this, sigma 1, sigma 2, and sigma 3. Has to be equal to this, yeah? So it's kind of finding the solutions for this problem. Basically, we said, well, so if I put this to this side and then I just subtract the matrices, so find me the solution for this. Well, definitely the solution of this system of equation, meaning what are the values of these elements, so this is 0. It cannot be that these are 0 because one of the properties of the direction cosines is that they follow this rule, so they are never 0. So this is a trivial solution, it does not exist. The solution is that the determinant of this matrix has to be equal to 0 to solve that system of equation, the determinant equal to 0. When I form the determinant, and there is also a lengthy process on how to get to this beautiful equation here, it says that, hey, you know what? You're going to find a qubit or a third-degree equation where if you solve that third-degree equation, it's going to give you 3 real roots, meaning that, the 3 roots are always going to exist. So if you're calculating the principal stresses and give you an error or some complex numbers, something is wrong. Okay, so 3 real roots are always going to exist, and they're going to be kind of based on these variables here, I1, I2, and 3. This is the way to calculate I1, I2, and I3, and these are called invariants of the stress tensor. They are named it that way because it doesn't matter the orientation of this cube, so you can orient it in any way. And if you take the same point, orient it differently, and calculate these values, they are always going to be the same. That's why they are called invariants of the stress tensor. This is beautiful. These are constants, meaning that there is only going to be a solution for the characteristic equation of the stress tensor, which means that if you have the stress tensor that you chose because you said, well, this is the way it needs to be done, and then you calculate each one of these invariants, input it in this formula, and take the roots of the invariant or of the equation, characteristic equation, it will give you the 3 principal stresses. This is a very nice procedure. All of this we have come is just to tell you this, that this is the way to to know what are the maximum, the largest stresses that point. Let's remember that's a point is going to have. If you change from that point to another location, this is going to be different. Any questions so far? All right. So how problems of this unit look like? It's something like this, like this. So, for example, actually this is just problem one because there are no more problems. If you have, and no, we're not going to deal with this in this semester. Oh, well, yeah, we're going to deal with this, but it's going to be presented differently. So if you have a stress tensor that you formed by calculating the loads and the location, moments, and everything, so you get to this stress tensor. And we will see how that's formed when we see failure theories. One of the tasks would be calculate the principal stresses, these ones here. Then, just to know the orientation and why the direction of those principal stresses. And why is important that? I bet you have seen this before when I show you this, but the concept of this. So let's bring this image here. So isn't it interesting that this piece of steel, brittle fracture, is always about 45 degrees? It always breaks at 45 degrees. If you take this angle here, it's more or less 45 degrees. And it always breaks like this if it's a brittle fracture. Have you wondered why? Well, imagine that you took a point there and you constructed your stress tensor here and here and here and have all of the arrows there. If you find the principal stresses, that's going to give you definitely this family here, yeah. If you find the orientation of these principal stresses, it's going to be, and I'm going to draw it here, that they're going to be oriented something like this, where the largest stress is going to be represented in this direction. And this is going to be, how much is the angle? Well, guess what? 45 degrees. Isn't this beautiful concept? So why would you like to know not only what is the maximum, the largest stresses, but the directions? Well, because you can infer how the thing is going to fail. And imagine that you're using welding. Yeah, you're welding something, and you want to guarantee that the welding is oriented in a proper way so it, let's say, withstands the largest stresses. So this is going to help you to do this. Another thing is kind of interesting to check for invariance, just to understand the concept that invariance, when you calculate the invariance of a stress tensor at a point, they don't change regardless of the orientation. And also, what are the normal shear stresses on a plane equal inclined to all three axes, for example, that would be on something. Or imagine that you have a design and you want to make sure that certain stresses at a certain orientation are not larger than something. Well, that's where you can do that. In the exercise classes, you're going to go over these topics. You're going to see principal stresses, principal directions, I think, normal or shear stress on a plane equal inclined, and also I believe you're going to have a problem on these ones here, on the translation equilibriums. But again, as a summary, it's not much. I mean, there is a lot of theory and concepts behind what we have just saw here. But when you clean everything, when you just leave what is the core of what you need to know, is that, hey, you know what? Whatever point I chose, there will be the largest stresses depending on the orientation I pick. Yeah, and this is kind of one of the things. So to summarize, so we already saw why we need stress tensor, because it's going to give us the ingredients to calculate stresses and to see if things are going to break or not, or are going to deform later by using some flexion theories or deflection theories. We saw what are positive or negative stresses according to the von Karman convention. We saw about the equilibrium conditions in rotation and translation, and we saw that rotation equilibrium give us two consequences: the reciprocity of shear stresses, and that instead of solving for 9 unknowns, we need to solve for 6. Then we know how to calculate, or we saw how to calculate stresses on an inclined plane that gave origin to determine, or to a formula that would give us principal stresses. And with that, we finalize our class today.